So, in this lecture basically we are discussing the coal based air process. In the last lecture we have covered the rotary kiln furnace based processes, and in this lecture I will cover the rotary hearth furnace based processes. Okay. So, based on rotary earth furnace, what is the rotary earth furnace? As I said, it is a donut shape reactor. You can see this is the donut, looks like a donut, and this is the inlet, this is the feeder end, and the solid charge moves in this way, and the solid charge is the rotating hearth. The hearth is there, hearth basically rotates, and the material is poured on the rotating hearth at the feeder end, and then the material is carried by the rotating hearth through different temperature regime. Suppose this is the preheating regime, one temperature, second temperature, and then this is the reduction zone. You can see it is yellow, this is the high temperature zone, and then it is again preheating, reduction zone, and then the cooling zone may be there, 1, 2, and then it is discharged from this end. So, this is there is the material moves 360 degree, and material moves 360 degree and passing through different temperature regimes and finally get discharged. So, this is the way material moves over the rotating hearth. Physically the material does not move, the material moves over the hearth and then it is discharged. And there are, you can find all the gas burners are there. So, here the basically the fuel is burned, gas fired furnace, basically gas is burned, and the gas moves in this direction in a opposite direction. The gas moves in the opposite direction to that of the, here the solid is moving in this direction, solid, and solid movement in this direction. Okay, I can just show you, that is the solid movement direction. Solid moves in this direction and the gas move in the opposite direction, gas in this direction, gas come in this direction. So, the solid goes in this direction and the gas moves in this. So, it is a counter current process, but again here the solid, the gas moves over the bed, over the plate bed. Okay. So, it is also a gas solid counter current process, and so during this movement solid basically gets preheated and then reduced and finally it's come out, and you can see the gas move in this direction. Okay. So, and then the gas finally come out to this thing. So, the gas first the reduction take place and then this gas is used for preheating, and after this gas, when the gas preheating the solid charge, it loses its energy, finally the waste gas come out. So, it is basically counter current process, so efficient heat exchange take place. Okay. So, it is the cross sectional view, you can see this is the burner and that is the hearth. And what is the feed material input? Input is basically the iron ore coal composite pellets or the briquettes, you can use it. Basically here the iron ore fines, directly iron ore fines you take, and the coal fines or iron bearing any solid waste fines you can take, and the coal fines any kind of coal, non-coking coal, and then you agglomerate them. And after agglomerating you can form the pellets or briquette, and these are basically naturally cured at room temperature, and also you can heat them to 200 degrees centigrade for some time such that the physical moisture goes out and it becomes little stronger also. So, too much of strength is not required, but some strength is required for charging. Some binder is also sometimes added to get sufficient strength such that during the charging they do not break. So, only charging, after that they do not have to physically move, basically the hearth will carry them. Okay. So, you are basically introducing the reductant inside the pellet. So, whatever is required is only supply the heat. If you supply the heat, reductant is inside, then in situ CO generation will take place because the carbon is there. If it gets the heat, it will basically carbon gasification reaction will take place. The CO2 will gasify the carbon to CO, and that CO will be used to reduce the iron ore, and during reduction whatever the CO2 will be generated, that will again gasify the carbon, generate the CO. So, it is a chain reaction. So, as a result you can reduce the iron ore. Okay. So that is the function is there. Okay, that is the way the reduction take place. And the final product is sponge iron or iron nugget. I will talk about that. Sponge iron you will get at the end, you will get the direct reduced iron, but you can get the iron nugget also. In that case, a part of the rotary earth furnace maintained at a very high temperature, more than 1300 degrees centigrade, such that the slag metal separation take place, and then during cooling, that is the iron nuggets forms. Basically, the slag metal how take place in this case at high temperature, the carbonized irons also melt and agglomerates, and during cooling they form the nuggets. Okay, and basically the slags squeezed out at the surface of the pellet. So, and then when you quench it, there is a cool it, there is a surface gets solidified on the surface and the liquid metal at the core, and then when you break it, you get the nuggets. Okay, so that requires a little higher temperature reactor zone, and also it is a little complicated process. That's why this process pilot scale is there for the nugget formation, but not much in the commercial front. Iron nugget is forming, but the sponge iron is highly commercialized. The stagnant charge, as I said, that's why you can compromise with the quality of raw material. Here also you can use any kind of raw material. Okay, lower CO2 emission. The CO2 emission it is less because you have because here the carbon and the ore are in intimate contact with each other, because you have mixed up the iron ore fines and coal fines. So, coal fines and the iron ore particles are in intimate contact with each other. As a result, the reduction kinetics is much faster and utility of the carbon is also much more. Because although finally it is a gas solid reaction by CO and CO2 gaseous intermediates, but since the carbon and the iron particles are very close together, the gas do not have to move a much distance, and the kinetics of the process is very fast, as well as you can utilize the carbon more effectively. So, as a result, the final CO2 emission is less. And limitation of the process is that since the heat is transferred, because as I said it is a cold composite plate, so you require the heat reactant is inside, but since heat is coming from the furnace to the bed, that is why this heat transfer by conduction over a thick bed is not possible. If the pellet bed thickness is very high, number of layers you put, then the heat cannot penetrate across the bed in the lower part of the bed. As a result, this lower part will remain unmetallized. So, that is why you cannot increase the productivity by increasing the layers. So, usually the commercialized process those are there, they operate with only a single or double layer pellet bed, not more than that. So, this limitation is there from productivity point of view. So, RHF based process, I will just talk about some of the process. One is called the Inmetco process. It is the international nickel company, they basically use this process Inmetco. Basically, they have converted their process to sponge iron production. Initially, basically they were used it for recover the nickel and chromium, cobalt from iron bearing solid waste. Okay. So, later on basically they have converted their furnace to sponge iron production, and they uses the iron based waste. That is why, because from the beginning they are utilizing the waste. So, their first aim from the beginning was to utilize the iron bearing waste material rather than the iron ore. So, iron uses the iron ore, iron based waste material as the feed. That is a new trend in the DR process. Okay. Uses binder to impart the sufficient strength for transporting to RHF without degradation. That is important, as I said. So, some kind of binder, because since you are using the waste material and you have to use some binder such that it has sufficient strength. So, uses some binder, and they use the 3-layer pellet bed, 30 millimeter thick, and complete post combustion of CO. Whatever the CO is generated from the direct reduction, they completely post combustion it, such that the your heat generation, that is the temperature of the furnace is higher. Okay, and also the coal volatile also burned inside it. So, furnace temperature is higher. So, if furnace temperature is higher, then you can transfer the heat at a much faster rate because temperature potential of the gas increases. So that is capable of supplying the heat to the solid at a much faster rate. Okay, that's why the 3-layer bed they can use. So they basically aim to increase the furnace temperature to a very high temperature, that the potential of the gas, heat transfer potential is increases such that they can supply the heat at a much faster rate, more efficiently. Okay. And also there, as I said, their degree of metallization they keep it to 70% like that. So they don't go, that's why they use a thicker bed. So metallization may not be more than 70%. So 70% to 80% is metallization. Then they can melt it into the some electric iron making furnace or submerged arc furnace, produce a synthetic metal, and then they can further purify it. Okay. So this is the in-metro process. Metallization here in this case they are getting 90 to 95% also. Okay. So when they use it like this, but depending on the raw material, what are the raw material they are using, okay, they cannot have the metallization up to very high. So when the very low grade ore they are using or low grade waste material they are using, obviously then this is the metallization, right. There is the metallization maybe 90 to 95%. That is the metallic iron to the total iron, that ratio is there, but it can contains lot of gangue. Okay. So lot of gangue. So total iron into the DRI may not be very high depending on the gangue content. These two things you have to understand. One is the metallization, it gives metallic iron to the total iron, this ratio. That means it depends on the reduction efficiency. If your reduction efficiency is good, you will get a good metallization. But the total iron in the sponge, it will depend on what is your raw material. If your raw material is bad, the total iron into the sponge will not be very high. The grade of the sponge will not be that good because it will contain a lot of gangue. So then if you want to remove that gangue, that's why you have used, there is an in-metro process previously we have discussed, then you take it to submerged arc furnace to eliminate the gangue. Okay, so that is important. Then comes the comet process, and the only plant is the Ellwood City, Pennsylvania, USA, 150 tons per day capacity. The comet process here, no pelletization is done. Comet process, dried iron ore and coal fines are charged as layers over the hearth, as layers, iron layers, then coal layers, then iron layers. Okay, and then you heat it, and then the coal will gasify, and then it will give the CO gas, it will produce the gasify the carbon, and that this carbon monoxide will move into the old layers, top and bottom, and then it will reduce the iron ore. Okay, that is the comet process. So high metallization they get because the process efficiency is good. Here also process efficiency is good, here also the process efficiency is good, metallization is high. And pilot scale plant is there, 1.5 ton per hour in Belgium. And they basically then modify this process. Basically when you have iron ore and coal in the layered fashion, so they are separated a little bit. If you just mix them, iron and coal fines, then their intimacy increases. So in the Steelmaking process, that was the idea. The mixing the ore and coal fines in RHA by mechanical device such that they become very intimate, your carbon utilization become more and the CO2 generation less, like that. But reduced carbon consumption, obviously carbon consumption was reduced but could not be commercialized because of some technical problem. This is the Steelmaking process. Okay. Then the dry iron Miami process, it is based on binderless briquette. That is the most important thing. They don't use the binder. So if they don't use the binder, then the strength of the material is a question, at least for transportation to the RHF and then this thing. That's why the furnace is equipped with unique charging and discharging system. That's why the charging system they have kept it such that the material does not break because it is a binderless briquette. They have some strength. They there is the briquettization process has some technology that gives imparts some strength, but it will not have too much of strength in absence of binder. So they make an unique charging and discharging system. use very fine iron oxide including byproducts of steel plant, even mud and the slurries to produce the briquette. So, this mud and slurries also gives some binding effect. Okay. Carbon to ore ratio is kept at 6:1. They can control the CO-CO2 ratio such that to minimize the deoxidation. This is very important, that is the gas overlying the solid burden should be reducing at least. As you know, that is the final stage, that is the Woodstite reduction. This is the final stage of iron oxide. Okay. And we have seen that at 900 degrees centigrade, if you want to reduce the Woodstite, the CO utilization is only 30%. That means 70% CO remains in equilibrium with the Woodstite iron equilibrium. 70% CO remains in equilibrium. So, if you have some metallic iron and you want to restrict its oxidation, then you have to maintain a 70% CO, at least 70% CO in the furnace atmosphere. Otherwise, if the CO percentage goes below 70%, then it will be oxidizing and then it can reoxidize the metallized iron. So, in the CO-CO2 environment, you have to keep more than 70% CO. I am just giving a theoretical idea. At 900 degrees centigrade, that is the from thermodynamic diagram we have seen. So, your CO-CO2 atmosphere has to be maintained. In this gas mixture of CO-CO2, percentage of CO has to be greater than 70%. So, that has to be maintained. So, that's why they have used the carbon to ore ratio. Carbon is very high, such that the CO in the gas, even after post combustion above, there is the CO over the pellet layer remains quite high. Okay. Product with 92 to 95% metallization is suitable for blast furnace feed. That is the metallization. They are basically charging it to the blast furnace feed as a blast furnace feed. You think is that the metallization is 90 to 95%, but since it is going to the blast furnace, that means the total iron is not very high, maybe. So, because of the waste material they are using, the total iron or the grade of the sponge may not be very high. So, they are basically giving it to the blast furnace feed. Because for use into the electric arc furnace, total iron is all an important point. You cannot, because electric arc furnace cannot handle too much of gangue. So, energetically and also that will make a problem, okay, efficiency wise. It is commercialized in USA and later Nippon Steel built 2 units at Hikari and then Kimetsu plant. So, it is there. So, this is about the dry iron process. So, another process we will go to, that is the fast melt process. Okay. This is then another RHF based commercialized process based on iron ore coal composite pellets. This is also based on pellets. Product containing gangue, and then whatever the product, sponge iron product, you just melt it in this called an electron iron making furnace. Electric iron making furnaces, basically it also maintains some reducing atmosphere such that it can reduce some amount of AFO that is left over after the direct reduction. Because in this case, fast melt process, whatever the metallized iron you get, okay, metallization may not be very high, 80%, then lot of AFO is there is the lot of iron is associated with the oxygen. So, you require some liquid state reduction also. So, that is why it melts the DRI, removes the gangue removes, also used for reduction of residual AFO in the DRI. Some residual AFO will be there, that you can reduce it. It also removes the sulfur and adjusts the carbon in the molten iron. So, you can just add some flux, you can make a basic flux reducing condition already there by carbon. So, you can remove the sulfur also. So, and adjust the carbon in the molten iron. So, fast melt process, the sulfur is very important because things are coal based process. So, sulfur is high. So, here in the EAF you can remove the sulfur too by making a basic and reducing slag just by adding lime and carbon. Handling FO has been found to be difficult as far as the refractory lining in the EAF is concerned. So, if you know that is the large amount of FO, it is very, FO reacts with the refractory. Okay, it has a propensity of reaction. So from ferrite it can form and all these things. So basically it has been become found to be difficult with as far as the refractory is concerned, large amount of FeO. Because in this case we are handling, because if metallization is not very high, so sometimes it may be 70 to 80% metallization, then when you melt it, lot of FeO will be there in the slag. So much of FeO in the slag, and that may be, and the refractory, they will react with the refractory. So because the FeO has a propensity forming the low melting eutectic for several oxides. So refractory oxide like MgO and the CO, it has propensity to combine with them. So it is very difficult, because when large amount of FeO there in the slag, it's very difficult to maintain the refractory. So that problem is there in the EIF. Then I will come to the last process, that is iron making technology Mark III. What is called iron making technology Mark I? That is the blast furnace, conventional blast furnace process is called the iron making technology Mark I. Then the direct reduction process, that is called iron making technology Mark II. And then the nugget production directly from the iron ore, that is termed as iron making technology Mark III, IIT MK3. Here iron ore coal composite pellets directly converted to the iron nuggets, not to the sponge iron. You can see there is a one compartment in the rotary earth furnace beyond the reduction zone, which has a much higher temperature, around 1300 to 1500 degrees centigrade, very high temperature. That is rare. So after reduction, slag metal separation take place at high temperature zone. Liquid iron gets accumulated in the core. So liquid iron, it is carbonized, so it can melt even at 1400 degrees centigrade. Okay. Liquid iron, because the iron is there in presence of carbon, so at high temperature it will get carbonized and it will melt also at lower temperature 1400. So once the iron melts, they will coagulate and they will form and they will be in the core at liquid iron. And the liquid slag oozes out, it is found, that is it comes out and the surface, and liquid iron there is inside. That is happening here. You can see it is reducing. After reducing, this the slag goes on the surface and inside you have the iron, and when you quench it, they become solidified. You can see iron nugget and the slag on the surface, and when you break it, the slag comes out and the iron nuggets also separates out. And it has the typical composition of 2.5 to 4.5% of carbon, 2% silicon, 0.1% manganese, 0.05 to 0.06 sulfur, and phosphorus rich. Okay, so this is a very promising technology, but it has a pilot scale plant in Meshabi, USA. It is called the Meshabi Nuggets also, but major problem is that this process has not seen the light of commercialization yet. So it is not producing in a large scale. Because of this process also, the raw material, it has some stringent raw material requirement is there, and process control is also there, and then anyway somehow this technology has not been commercialized successfully. In the pilot plants they have produced the iron nuggets. Okay, so I am coming to the end of coal based DR processes, and you can consult the book of Amit Chatterjee, very nice book there on the sponge iron production by direct reduction of iron ore, New Delhi. And you can also consult the book of Iron Making, Steel Making by Ghosh and Chatterjee. Now I come to the conclusion. So first is coal based process you can classify into two broad categories. One is the rotary kiln based process, and another is called RHF based process. Besides some other process also we have discussed, like sarcophagus process that is based on fluidized bed, and Primus process that is based on multiple hearth furnace based process. But rotary kiln process is the most widely accepted process and most rugged process, and RHF process also has some future prospects. Okay. As I said, rotary kiln is well proven and very rugged technology, but it has capacity is 500 tons per day. So, if you want to produce more, you have to use number of multiple of such reactors, and then you can produce more. So, their initial investment cost is less, but specific there is the expenditure. There is the expenditure per unit mass production is much higher, and their productivity is not very high compared to the shaft furnace. Shaft furnace can produce 5 times than that of the rotary kiln process. But the rotary kiln process uses non-cooking coal. That is the advantage. It can uses the non-cooking coal in place of the costly natural gas. Okay, gas-based process you have to use a natural gas. Also in India, especially in India, we do not have much of natural gas. We have some offshore natural gas in Bombay High. Otherwise, we have plenty of non-cooking coal. So, we can use that cheap non-cooking coal in the rotary kiln process. That is the major advantage of rotary kiln. And rotary kiln process more disadvantage, or as I said, major disadvantage is that it is a very polluting process. So, unless we separate the dust from the waste gas, this process is not at all sustainable. Second thing is that waste gas also contains significant amount of energy, around 40% of the input energy in the waste gas. So, you have to utilize it for power generation, otherwise economically this process also may not be viable. But the major advantage of the rotary kiln process is that they are proven and rugged reactors. They can use any kind of raw material. There is the non-cooking coal and inferior grades of raw material. You can iron ore, you can use it. And most widely used process is Lurgi-SLRN process, but India, since it is a very prevalent in India, this rotary kiln furnace based process, and different companies, private companies in India has developed their own technology. Okay, so patented technologies are there like TDR and then GSW process, OSIL, like that SIL. And RHF process is very promising from this point of view. It can use the iron bearing any kind of solid waste. That's why the RHF process will be very prominent in future days, because it has the capacity of using iron bearing solid waste, any kind of. And the advantage of RHF process, as I said, the material physically does not move. It is the rotating heart that basically carries the material through different temperature regimes and reduce it and then produce that sponge iron. Okay. So, that is why the quality of raw material can be compromised. That is why you can use any kind of waste fines and then non-cooking coal, we can mix them and make pelletize or briquettize, and after that you can reduce it into the rotary hearth furnace. Okay. So, and then finally the metallized, that is the sponge that is obtained. It can contain a lot of gangue with low total iron. Okay, then what you can do, there is basically this type of sponge iron, maybe the sponge iron grade may not be very high because the total iron may be less because of large gangue content. Then they can be melted into the what is called the electric iron making furnace, so where you can separate the gangue, where you can reduce the unmetallized FeO to iron. Okay. So, produce it. So, major advantage why the RHF will find a scope, because it can utilize the solid waste and the reactor is such that, so we can compromise on the quality of the raw material. So, that is the advantage of the rotary earth furnace. And high temperature based rotary earth furnace, that is the Coves ITMK3, that can produce the iron nugget. But this is a very nice reactor, that is if it could find the day of commercialization, if it can be commercialized, then it will be a very nice process. So, RHF furnace, RHF based process is the ITMK3 is a very promising process, and hopefully in near future it will be commercialized. Okay, thank you very much.